Hello everyone, I am Ermiya Farokhnejad. I'm going to talk about one of my recent papers, a fully dynamic K-median with near optimal update time and recourse. This is a joint work with Sayan Bhattacharya and Martín Costa. Let's start with the problem definition. In metric K-median problem, we are given a weighted metric space together with an integer k. And the goal is to find a subset of this metric space of size k, and then each point is going to be assigned to its nearest point in this subset. The points of this subset are going to be called centers. So we want to pick k centers, and then each point is going to be assigned to its nearest center. For instance, here, if we have this space, and let's say k is 2, it is possible to consider these two red points as centers, and then each other point is going to be assigned to its nearest center. And the goal in K-median is to minimize this objective function, the distance of any point to its assigned center times the weight of that point, and the summation over all of the points in the space. The setting that we consider is that we have access to the distance of any 2 points in the space as an oracle in just constant time. So we have an oracle, we can ask what is the distance between P and Q, and we assume that we have this distance in just constant time. This is the setting that we consider. Metric K-median is one of the fundamental problems in K clustering in general. For instance, you can see that in this book, there are many sections related to K-median. What do we know about K-median? We know that it is possible to get constant approximation in tilde of K and time. And in order to get any constant approximation, we need at least K and time. It means that if the running time of the algorithm is little o of kn, then the approximation ratio is not constant. All right, now what happens in the dynamic setting? In the dynamic setting, the input space is changing. So we have a current space, and the algorithm has a solution on this space. Now an update comes to the algorithm. What does it mean? It means that a new point is going to be inserted to the space, or some point is going to be removed from the space. After this update, the algorithm is going to change its solution. The algorithm is going to insert some new centers into U and remove some of the previous centers from U in order to come up with a new solution for the new space. Now, what is update time of a dynamic algorithm? The update time is the running time that it needs in order to handle one update in the space. And what is the recourse of a dynamic algorithm? The recourse is the number of times that the algorithm changes its solution. How many points are inserted to the space and how many points, to the solution, and how many points are removed from the solution. This is called recourse. What is the goal in dynamic K-median? The goal is to find an algorithm that has good approximation ratio, a small update time, and a small recourse at the same time. This is the optimal that we can hope for. First of all, this tilde notation hides polylogarithmic factors in n and delta, where n is the maximum size of the dynamic space P, and delta is called the aspect ratio of the space, which is the ratio between the maximum distance of any 2 points in the space by the minimum distance of any 2 distinct points in the space. And this is optimal up to polylogarithmic factors. And now let me explain that why this is the best that we can hope for. Well, we know that it's NP hard to find the exact solution, so we have to find approximation algorithms, and the best approximation is going to be constant. For the update time, since we know that in the static setting, it's not possible to get constant approximation with little o of nk time, it concludes that in the dynamic setting, we cannot hope for little o of k update time. Why? Because you consider that we have an algorithm, a dynamic algorithm with update time u. What we can do is to design a static algorithm with running time n times u. How to do that? By just inserting points of the space one by one. So at the end, the solution of the dynamic algorithm after inserting all of the points in the space is going to be a good solution, a feasible solution for the final space. And since the number of insertions is going to be n, total number of points in the space, then this is going to be a static algorithm with running time n times u. Since we know that it's not possible to get constant approximation with less than nk time, then this shows that any dynamic algorithm should have at least omega of k update time. So this means that tilde of k is actually near optimal up to polylogarithmic factors for the update time. And for the recourse, assume that some adversary inserts a point far, far away from the current space. If we want to have constant approximation, according to the objective function, we should consider this new point as a new center in our solution. It means that the recourse of the algorithm is at least 1 per update. This means that tilde of 1 is actually optimal up to polylogarithmic factors for the recourse of the algorithm. So this is the best that we can hope for any dynamic algorithm. If you look at the prior work, you can see that none of them get all of these guarantees at the same time. Even the best one does not achieve all of the near optimal guarantees at the same time. Now what we showed is as follows. We showed that there exists an algorithm for dynamic k-median that achieves constant approximation ratio, tilde of k update time, and tilde of 1 recourse, or more specifically, order of log squared delta recourse. And to give you some more information, the algorithm is randomized. It works against adaptive adversaries. The update time and recourse hold in amortization, and all of these guarantees hold with high probability. This is our result. All right. Now I'm going to talk about some of the building blocks that we use from the prior work in this paper. I start with 2 simplifications. The first one is called improper k-median. The setting that we consider is that there exists a ground metric space, which is a static metric space, P star, and the dynamic space is always a subset of P star. And now the algorithm can open any center from anywhere in the ground metric space. So the solution of the algorithm, which is U, is not necessarily a subset of the dynamic space. It can be a subset of the ground metric space. This is called improper k-median. And prior work showed that if we have an algorithm for improper k-median, then we can achieve an algorithm for the proper k-median with a small overhead on the approximation ratio, recourse, and update time. So morally, we can assume that the algorithm can open any center from anywhere in the space, which is not inside the current space. It can be anywhere in the ground metric space. This is the first simplifying assumption that we consider. The next one is called sparsification. Assume that we have an algorithm whose running time, whose update time is tilde of n. From sparsification techniques, it is possible to show that we can get an algorithm with tilde of k update time instead of tilde of n. And again, we are going to have a small overhead on the approximation ratio and recourse. And again, here, morally, we can assume that the size of the space, the maximum size of the space, which is n, is going to be at most tilde of k. So in the future, I will show you how to get tilde of n update time. And because of this sparsification, it can be reduced to tilde of k. Next lemma that we are going to use from prior work, which is very important, is called lazy updates lemma. Assume that we have 2 spaces, P and P prime, 2 metric spaces, such that their symmetric difference is at most S. Then it is possible to show this inequality. What is opt_k? Opt_k is the optimal improper k-median objective on this space P. The optimal improper objective function. And now lazy updates lemma says that this inequality holds. And let me tell you a little bit about the proof. Let's say that V is the optimal solution of size K in P. So this is V and this is the space P. and now consider the space P prime such that the difference of P and P prime is at most S. What we can do is as follows. We can assume that all of the points that are inside P, but not in that are inside P prime, but are not in P, and insert all of them into V. So we get a solution V prime, which is a feasible solution for the K plus S median in the new space in P prime. And now, since we have inserted all of the points that are inside P prime, but not inside P, into the solution V, it means that none of these points incur any new cost to the solution, incur any new cost to the objective function. So the cost of V prime on the new space P prime is at most cost of V on the space P. So this shows the lazy update lemma. The next lemma that we are going to use is called projection lemma. What I'm going to tell you here is not actually the projection lemma. It's going to be some conclusion of the projection lemma, which is more intuitive. And what is it? Assume that we have a solution U, which is an alpha approximation of optimum K median, but the size of the solution is more than K. Then it is possible to show that there exists a subset of U, like U prime, whose size is exactly K. And again, it's a good approximation. It's alpha plus 2 approximation. This means that if we have a solution which is already good, but its size is greater than K, it's not feasible. It is always possible to remove some of the points from this solution to reduce the size to exactly K, and again, have a good approximation for optimum K median. This is one conclusion from the projection lemma. All right, now I'm going to talk about some of the key insights in our paper, some of the main contributions of our paper. Let me start with the general framework of the algorithm and tell you about the challenges and how to bypass these challenges. First of all, I'm going to define the redundancy of the space. The redundancy of points at P is going to be an integer R such that these two inequalities hold. Intuitively, you can assume that if the redundancy of the space is R, intuitively it means that there are K minus R many points, K minus R many parts of the space that are far from each other. Let's say their distance is infinity, and the distance of any 2 points inside one part is going to be small. This is the intuition of redundancy that you can consider. All right, now what is the framework of the algorithm? The algorithm works in epochs. The length of the epoch, we start at time step 0, and the length of the epoch is going to be the redundancy of the space. R is the redundancy at time step 0. Now we find a solution of size K minus R in this time step 0. Let's say U0 is a solution for optimum K, is an optimum solution for K minus R median in this space. And then we can do lazy updates for R many steps. What does it mean? It means that if a new point is inserted to the space, we can just open this point as a new center. And if a point is removed from the space during these R updates, we don't change our solution. And we can do this because we are considering the improper K-median problem. And then we can repeat this process from time step R plus 1, which means that at that time step, we find the redundancy of the space, that is the length of the epoch, and we continue this process. All right. There are some challenges here. The first challenge is that also we have inserted all of the points during the epoch to our solution. We know that these points does not incur any new cost for the objective function. But in order to show that the algorithm has constant approximation ratio, we have to compare the cost of the solution with the optimum K-median in that time step. But in the fully dynamic setting, we don't know how the optimum K-median changes. It can go up, it can go down. So we don't know how to show that the solution UT, the cost of this solution, is within a constant factor of opt K on that space, on space PT. We don't know because the opt K of the space PT might be very small. And we don't know how to analyze that if we consider just this framework. And the second challenge is that if you consider the time step r+1, in that time step, we are going to start with a brand new solution of size k minus r prime, let's say, where r prime is the redundancy of that space. And this solution might be very different from the solution of the algorithm at time step r. So here we have a large recourse. So we need something in order to bypass this. Well, in order to bypass the first challenge, where the value of opt can change, we use some new lemma, which is called double-sided stability lemma. I defined the redundancy in previous slides. Now I define a new notion, which is called stability. What is the stability of point set P? It's the maximum integer s, such that no matter how you change the space by s many points, the value of opt k does not change by more than a factor of, let's say, 4, by more than a constant factor. Now what we showed is as follows. We showed that the stability of the space is always theta of redundancy of the space. One side of the inequality, which says that redundancy is always greater than stability, follows from lazy update lemma, and I'm not going to talk about that. But I'm going to talk about this side of the inequality, which says that stability is always omega of redundancy. For this part, we consider the LP relaxation, the well-known LP relaxation for K-median problem. We call this fractional K-median. The first fact about this fractional K-median is that if we consider the optimum solution for this LP, which we denote by f opt k, if we consider this function as a function of k, then it is a decreasing and convex function. This is the first fact that we figured out. And the second fact is that the integrality gap of this LP relaxation is constant. It's at most 3. If we combine these two facts together, we can show this side of the inequality in the double-sided stability lemma. To give you some more detail, let's say that this is the f opt, which we know that is convex and decreasing. And let's say the value of opt k is lambda. Since the redundancy of the space is R, it means that if we consider the opt k minus R median, it's going to be at most 4 lambda. And now consider the right-hand side. Consider the optimum k plus R by 6 median. Since the function is convex, you can see that the value of the opt at this point, k plus R by 6, is going to be at least lambda by 2. Now, if we combine this with lazy update lemma, it shows that no matter how you change the space by R by 6 many points, the value of opt k is not going to drop by more than a factor of 2. And this shows that side of the inequality where stability is always omega of redundancy. And this shows the double-sided stability lemma. How to bypass the second challenge that I told you in order to have a small recourse? We use the notion of robust centers that is defined in the previous work. I'm not going to talk about these robust centers in this talk, so assume this as a black box property. So we call a set of centers robust if it has some property, and we use this as a black box. And what is the main property of these robust centers? We showed a new property for these robust centers as follows. Let's say that U is a subset of K, is a set of K centers that is also robust, and it's also 8 approximation for optimum K median. Then for any integer L greater than 1, it is possible to show that there exists a superset of U of size redundancy plus L plus K, such that it's a good solution, a 3 approximation for optimum K plus L median. So this says that you can always insert redundancy plus L many centers to a robust solution in order to get a constant approximation for optimum K plus L median. Note that this is not always correct. U should be robust. This is one of the main points. And to give you an intuition why this is correct, let's say R is the redundancy of the space. Since R is the redundancy, intuitively it means that there are K minus R parts far away from each other. Let's say their distance is infinity. Now let's say U is the robust centers. We know that it's 8 approximation, so this solution U should hit all of these parts. And now let's say V star is the optimum K plus L median in the space. If one of these parts contain more than one blue center, we call these blue centers non-trivial centers. And if one part of these K minus R parts has exactly one red center and one blue center, then since these are far away from each other, it's easy to see that you can swap the red center and blue center, which means that if a part contains exactly one red center and one blue center, the red center is going to be as good as the blue center. All right, now consider the solution U and insert all of the non-trivial centers to U. First of all, it's easy to see with some easy counting argument that the number of non-trivial centers is at most R plus L. So the number of centers that we are inserting to U is at most redundancy plus L. So the size of V, which is U plus all of these non-trivial centers, is a small. And why V is a good approximation for optimum K plus L median? Because in any part that contains more than one blue center, we have already inserted all of these blue centers. So the cost of this solution is equal to the cost of optimum solution in that part. And in the other parts that contains exactly one red center and one blue center, because U is robust, then this red center is a 3 approximation of the blue center. And finally, in the reality, we know that this is not always the case. The redundancy of the space might be R, but it's not always correct that these parts are far away from each other. So they can be close to each other. And the notion of robust centers is something that tries to achieve something like this. Is try to achieve something like that. We can consider that the parts are far away from each other. All right. Now I'm ready to explain how to get constant approximation ratio and polylogarithmic recourse. In this part of the talk, I don't talk about running time. So we assume that we have exponential running time in this part. Consider the same framework. The algorithm works in epochs. At time step P0, we call the space P init, and we call the initial solution of the algorithm, at that point, U init. We assume that this solution, the initial solution, is a robust solution and it's 8 approximation. Now, what is the length of the epoch? The length of the epoch is going to be S, which is the stability of the initial space. So first of all, we find the stability of the space, and this is going to be the length of the epoch. Now, consider that P final is the space at time step S plus 1. So we have this picture. What to do during the epoch? First, we start with a solution of size K minus S, which is a subset of U init. And then we can do lazy updates for S many updates. We have a solution of size K minus S. Anytime a new point is inserted, we insert it to U0 as a new center. And if a point is removed, we don't change our solution. So during time step 0 to S, we have a feasible solution. Now what to do at the end? At the end of the epoch, let's say L, let's define L to be S plus 1. At the end of the epoch, how to find a good solution for P final? We do the following. In the first step, we insert some points into U init in order to get a 3 approximation of optimum K plus L median in the initial space. So we find a U star, which is a superset of U init, like this. And the number of new centers that are inserted to U init is going to be theta of redundancy plus L. Because we know that U init is a robust center, this U star exists because of the property of the robust centers. So we can find this. What's the next step? In the next step, we insert all of the points that are in P final but are not in P initial to the solution U star and get the solution V star. This is because we don't want any new point to incur any new cost to the solution. So currently we have a solution V star which looks like this. And what is the cost of V star? Well, cost of V star is in this final space is at most going to be cost of U star in the initial space because we have inserted all of the new points as new centers. This is lazy update lemma. And the cost of U star is also 3 approximation of opt k plus L in the initial space because of step 1. And again, because of lazy update lemma, this is going to be at most 3 times opt k in the final space. It means that the solution V star is now a 3 approximation of optimum k median in the final space. But the only problem is that the size of V star is now greater than k. So what we have to do in the next step is to reduce the size of V star to k. So we find a solution, U final, like this, which is a subset of V star, and this minimizes the cost of this solution for the objective k median. And according to the projection lemma, it is possible to show that this U final, the cost of the solution is at most 5 times optimum k median. So we have a solution U final, which is a feasible solution of size k, and its cost is exactly 5. It's at most 5 optimum k median. It's a 5 approximation. And finally, since the solution is changed, we don't know whether this solution is robust anymore. So we have to make this solution robust in the final space. And in order to do this, we use a subroutine called robustify. And I'm not going to talk about this subroutine because we are considering robust centers as a black box definition. And after this robustify, the final solution is robust, and it's possible to show that the final solution is again 8 approximation. So we have this property that the solution is robust and 8 approximation. That is the property that we had in the initial space. This means that now we can repeat this process from time step s+1 and go further. And this is the entire algorithm. And I explained why the approximation ratio is constant. Now let me explain why the recourse is also good. Well, during the lazy updates, you can see that the recourse is at most 1 because we are at most inserting 1 center per update. What happens at the end of the epoch? In step 1, we are going to insert redundancy plus L many points into U init. According to the double-sided stability, we know that the redundancy is theta of stability. And L is also S+1. It means that the size of U star is going to be K plus order of S+1. What is size of V star? Again, the number of points that we are inserting into U star, which is P final minus P initial, its size is at most S+1. So the size of V star is again K plus order of S+1. Now consider U final. U final is a subset of size K of V star, and U init is also a subset of size K of V star. So the difference between U init and U final is going to be at most order S+1. So since the length of the epoch is S+1, this is just order 1. This is just constant in amortization. So we have constant recourse in amortization. But in the last step, in step 4, when we are calling robustify, it is possible to show that this robustify actually has an amortized recourse of order of log squared delta. You can find this in paper, and I'm not going to talk about this. So the final recourse of the algorithm is going to be order log squared of delta in amortization. And finally, let me talk about how to get fast update time for the algorithm. In order to do this, we need 2 subtasks or 2 subproblems that first we have to solve them. One of these subproblems comes from previous work, and the other one is our contribution. So let's start with this restricted K median. What is this problem? Assume that we have a center set U of size K, and the goal is to find a subset of this of size K minus S while minimizing its cost. So we have U and the space P, and the goal is to remove as many centers from U to get U prime while minimizing the cost of U prime. Previous work shows that it is possible to get constant approximation for this problem, restricted K median, whose running time is N times S. And we are assuming that we have access to some auxiliary data structure. And what is that data structure? It's as follows. We consider that for any point in the space, we have the sorted distances of this point to all of the centers in some binary search tree. If we have this auxiliary data structure, then we can solve this restricted k-median in ns time to get a constant approximation. This comes from previous work. Now, what is the other problem? The other problem is augmented k-median. This is the opposite side of restricted k-median. We have a solution U and a space P. Solution U is of size K. Now the goal is to insert as many centers into U in order to get another solution U prime while minimizing the cost. And here we showed some similar result. We showed that it is possible to get constant approximation for this problem, again, with running time n times s. And again, we need access to this auxiliary data structure, which is the sorted distances of any point to all of the centers. Let me explain a little bit how this works. Let's say this is the space and the solution U. The goal is to contract all of the points in the space U into a single point and then try to solve a s+1 median problem that contains this point. So first of all, we contract all of the centers in U to a single point U star. And now we define a new metric in this new space. The metric is as follows. The distance of any point to U star is exactly the distance of X to entire U in the previous space, original space. And the distance of any 2 points X and Y is the minimum of the real distance of X and Y in the original space, and the distance of X and Y if you go from X to U star and go from U star to Y. It is possible to show that this new distance function is actually a distance function, and it defines a metric. And now what we can do is to solve an s+1 median in this new space, and the only constraint is that this solution should contain U star. And in order to achieve this, we can simply define the weight of this U star to be infinity. If we do this U star should be inside the solution. So the algorithm is as follows. We define this new metric, and then we solve any static s+1 median in this new metric space. And the running time would be n times s+1. All right, now I'm ready to explain the final algorithm that achieves fast update time. Recall the algorithm. First of all, we have to find the stability of the space, which is the length of the epoch. How to find S? We start with computing a constant approximation of the redundancy of the space. And how to do this? For every I, we find an estimate of the value of the optimum k-2 to the I median. We use restricted k-median. So we have this U in it. We remove 2 to the I many centers, and we have a solution which is a constant approximation of optimum k-2 to the I median. This is because we know that U init is already an 8 approximation for optimum k-median. So because of projection lemma, there exists a subset of this, which is also a subset of this of size k-2 to the I, which is a constant approximation of optimum k-2 to the I. So with restricted k-median, we can have an estimate of this value, optimum k-2 to the I. Now we can stop this process whenever this estimate is way larger than optimum k-median. Assume that we have stopped at iteration I star. It means that 2 to the I star is now a constant approximation of the redundancy. Finally, we set the value of S to be this 2 to the I star divided by a large constant. If we define this with the double-sided stability, it is possible to show that the space is going to be S-stable, and S is going to be theta of redundancy, and it's going to be theta of stability of the space. So S is a lower bound for the stability of the space, and it's also a constant approximation of the stability. What is the running time here? Well, the amortized running time is going to be tilde of n because of the double-sided stability. We know that redundancy is theta of stability, and all of these parts is done with restricted k-median, and the running time is going to be at most tilde of n times the redundancy. So the amortized running time is near linear in this part. So far, we have found the stability of the space, which is the length of the epoch. What's the next step? The next step is to do lazy updates during the epoch. We have to start with a solution of size k minus s of U init. How to find this solution? Again, we use restricted k median. If we use restricted k median, we can find U0 in times n times s. And this is going to be tilde of n in amortization because the length of the epoch is s plus 1. Now, what to do at the end of the epoch? Recall that the step 1 is to insert redundancy plus L many centers into solution U init. How to do this, how to find this U star? We can find a constant approximation of U star with using augmented K median, right? Because augmented K median is trying to insert some points into U init. And the running time is going to be tilde of n times the number of points that we are inserting. And again, because of double-sided stability, redundancy is theta of stability, so the running time of this part is n times s plus 1. And since the length of the epoch is s plus 1, the amortized running time is going to be near linear. Yeah, this works because of double-sided stability, and the amortized running time is tilde of n. What's the next step? Next step is to insert some points into U star to get V star, which is all of the points that are inside P final that are not inside P initial. Well, it's easy to see that we can do this in just constant time. It's trivial. Next step is to reduce the size of V star to exactly K. So we want to find a subset of V star of size exactly K while minimizing the cost. How to do this? Again, we use restricted K median. If we use restricted K median, the running time is going to be n times the number of removed points, which is size of V star minus K. And you can see that this is tilde of n times s plus 1. And again, since the length of the epoch is s plus 1, this is going to be near linear in amortization. And what's the last step? The last step is to make this final solution a robust solution in the final space. Since I haven't talked about this robustify subroutine, you can see this in the paper that the amortization running time of this subroutine robustify is, again, near linear, tilde of n. So the amortized running time of the entire algorithm is going to be near linear. The final conclusion is that there exists an algorithm for dynamic K median, achieving constant approximation ratio, tilde of K amortized update time, and order of log squared delta amortized recourse. This is the final result. Thanks everyone for listening to this talk.